So, do not question what this is. I promise this makes sense, welcome to a revision stream. So what I thought I would do is we are getting scarily close to A-levels, and it feels like I've been slacking this year. I mean, I've gotten some decent grades, like I've done quite well, but I feel like I'm slacking in terms of revision. So what we are doing is I want to make it so that we try and do at least 3 of these streams every week. So some days we might be doing biology revision, some days it might be history revision, just kind of doing what we can when we can, really. Because, we are getting close to exams, we don't have a lot of time, so I really want to start to hammer in this revision. And one topic that I haven't done in a couple of months properly is biological molecules. Because I personally think it's the easiest topic out of everything in biology, but we haven't done it in a while. So let's give it a go, let's see what we can remember. And then next time I do one of these streams, which won't be tomorrow, maybe Wednesday or Thursday, I will attempt to revise the cells topic, which obviously contains things like mitosis, microscopy, immunology, things like that. So let's crack on with biological molecules. This shouldn't take too long, maybe like 40 minutes or whatever. Also, my hair is a massive mess today. Don't know why. Anyways, let's crack on with this. Let's start off with everybody's favourite, carbohydrates. Carbohydrates. So, just a sec. There we go. Okay. So, carbohydrates. Basically the energy storage molecule. The big thing we need to know about this topic right away is what hydrolysis and condensation is. Hydrolysis and condensation reactions. So, hydrolysis is where you are adding a water molecule. Condensation is where you're removing a water molecule. And what this does is it creates bonds. For carbohydrates, the bond type that we're looking at is going to be glycosidic. So, glycosidic bonds, a hydrolysis reaction will break apart. A condensation will combine or bond. So, let's go into specifics now. Let's look at 2 isomers. For those that don't recall what isomers are, they are, I believe the official definition is like molecules with a different arrangement of atoms, or basically it has a different arrangement of molecules, but it's a different arrangement, but it contains the same molecules. So this is going to be beta glucose. And these are pentose sugars, they're both pentose. This is going to be alpha glucose. So these are isomers. Okay. Now let's look at some specific examples of, let's look at some combinations. So, glucose plus glucose, glucose plus galactose. I always forget sucrose, maltose, fructose, that's it. So, glucose plus glucose is going to give us I want to say maltose. Glucose and fructose, I think, is sucrose. And glucose and galactose is lactose. I might be wrong there. I might be wrong. But that seems about right. We can quickly talk about the Benedict's test. There's two types. Type 1 is for reducing. Non-reducing, i.e. sucrose, I think is one. Basically, for both of these, let me move that back a tad. Oh, the camera. Hopefully that's fine. For the reducing test, need a different color. This one is incredibly easy. I think the mark scheme literally has it where it's heat and add Benedict solution, and a positive result is indicated by a red precipitate. For the non-reducing, it's a tad more complicated. You have to heat with acid. Then you have to neutralize. Then you have to add Benedict solution. But the exact same as said, it's a red precipitate. It kind of functions similar to like a scale, where red means that there's a high concentration of reducing or non-reducing sugars. Orange, you know, a moderate concentration. Yellow to green would be like a light concentration. The idea here, though, if you wanted to explain this in an exam, let's say on paper 3, which I want to look at paper 3. I want to figure out what questions they ask you, whether you would get asked about this practical in that paper or not. One thing to note is why you do this. You would heat so that... I don't recall why you would heat, but logically speaking, if you wanted to heat it up, it's likely because then it'll work faster, you know, the solution. You add acid for the non-reducing because it breaks apart the glycosidic bonds, hydrolysis. Neutralize because the solution can't work in acidic conditions, so you add something like, what's an example? Is sodium hydroxide an alkali? I think. So you would add that to neutralize it, and then, yeah. So that's for Benedict's test. For reducing and non-reducing. There is, of course, everybody's favourite, the potassium iodide test. This one is very easy. You literally just add potassium iodide to starch, and it will turn a blacky blue colour if said starch is present. That's basically all there is to it. Let's look at the structure of starch, because it is a storage molecule, and I'm trying to recall, is that the one with amylose and amylopectin? It is. Starch. Starch is a very important storage molecule. I do not recall which one is which, amylose and amylopectin. One of them is highly branched and short. The other one is coils. And I sound a bit delusional saying that, but I promise it's right. Let's just draw. Again, I can come and correct this another time, so it's okay. Amylose and amylopectin. This one is highly coiled so that it increases the surface area, basically allowing you to tightly pack more of this molecule in. Amylopectin, on the other hand, is highly branched to once again increase the surface area for a faster hydrolysis. That's the gimmick. Faster hydrolysis because of its increased branches. We could take a look at the other two, which is going to be cellulose and is it glycogen? Cellulose is once again only found in plants. Trying to lift that up a little. Oh, come on. Hopefully that's fine. Cellulose is once again only found in plants. It is a very unique molecule in the sense that it is bonded by cross-linking hydrogen bonds, which form strong microfibers. They are arranged in straight rows, which do not coil, do not branch. And you smell microfibers, microfibrils, which is kind of odd, but hey, I'm not a, linguician. Glycogen, on the other hand, is literally just an incredibly branched molecule. Which obviously is going to lead to faster hydrolysis. And remember, these molecules are made of glucose, okay? They are storage molecules for glucose. That is the entire point. In fact, let me redo this quickly. So yeah, glycogen is only found in animals as well. And starch is only found in plants. Okay. I am trying to recall if there is anything else we need. What are you on about? Okay, is there anything else we need to know? 2 notes. Number 1, the Benedict's test is a qualitative test. What that means, in summary, is you're looking at colour, okay? Your own eyes are looking at the colour of precipitate, which means it's subject to interpretation. Similar to the ELISA test where, the enzyme is attached to the antibody, which in itself is attached to an antibody, which in itself is attached to an antigen. That enzyme, you add the solution to it, and it will create a colour change, similar to this, where you're looking at a coloured precipitate, which means it's subjective. In order to verify how exactly, the concentration, there are 2 methods that the exam wants you to know about, but we never learn in school. We never learn these, and that's why people always lose marks on that question. The method that they want you to talk about here is literally use colorimetry. So that would be, getting a calibration curve or something, basically being able to plot exactly what color it is, where literally just filter it out, wait, and depending on the mass, you are going to be able to determine. So you would need to use a balance. You would use a balance, and that would allow you to figure it out. So that is literally everything that I can recall for the carbohydrate topic. I am trying to recall if there is a single other part of this topic. Should we quickly go on to doing the respiration? Can we link this to respiration real quick? Because it's all fun and games talking about glucose, but if you can't actually see the functionality of glucose, then what is the point? So you know what? I hope that has provided some use. Let me just sit back there, take a screenshot of that for everyone. Okay. So, we'll move on to the... And I haven't done this in a while. I haven't done this in a very good while, so let's see how much we remember. We're back, okay. So, how do we start this? It's respiration, so you're converting glucose, a 6-carbon compound, into ATP, NAD, and FAD. No, NADH, FADH. Okay. Okay. So we're looking at the oxidative phosphorylation, the Krebs cycle. Yeah. What are the other two stages called? Stage 1 and 2. Glycolysis. Okay. Right. Glycolysis. Okay. Oh, wow. Okay. This has really given me a run for my money. I was very good at this topic a couple of months ago. I don't remember shit now. Oh my god. Okay. See, this is why it's important to revise year 13 content. Because year 12 content I know so well, aside from one or two minor topics, like obviously, you know, the ecology topic is shit. The genetic topic is a bit of a piss take. You know, I think things like digestion is a bit of a piss take. But I'm getting there with that topic. And even the general cell topic can be a bit of a piss take with how wordy it is. But the year 13 content, we have not had a mock for. We don't really know what we're doing. So, yeah. Let's try and get this. So, while I was talking, I was just trying to remember it. 6-carbon compound glucose. Oh, the investment stage. Okay. Quickly, I remember this. It is broken down into a 5-carbon compound, I want to say. I don't recall what you call it. But this uses ATP. Oh. I know by the end of this, it becomes pyruvate. How? How does it become pyruvate? Is it? Okay, I'm gonna have to go downstairs and grab my computer for this. This is my guess. This is a complete guess. Is it a 4-carbon compound and then 2 3-carbon, which produces ATP? Okay, you know what? I feel like that is somewhat accurate. Let's carry on from here. I don't recall what this stage is called, so I'm just going to put that I don't know. But this stage is where you have a 3-carbon compound pyruvate. You combine that with, is it acetate? And it becomes acetyl coenzyme A. Which again, I think is a 2-carbon compound. And at this point, I think there is a NAD converted to an NADH, which is oxidation? Reduced NAD. It's reduced. Because it's... Oh, oxidized. Okay. Oh, but then where does FAD come in? I don't think there's an NAD reduction here. Then it's the Krebs cycle. Oh, no. Okay. I will go downstairs and check this now because I do not recall. But, from what I remember, it makes 2 NAD... H. It makes 1 FADH. I think it makes 2 ATP. I will go check. I will be right back. Gulp. Okay. Right. So, from my memory, glycolysis is where a 6-carbon compound, glucose, is broken into a 5-carbon compound. That's called decarboxylation, right? Maybe. Yes, because then it's oxidized, which causes that to become reduced NAD. It then splits into 2 3-carbon compounds. It's the investment stage, so 2 ATP minus 1 ATP net product. I'm missing something here. Feel like I'm missing something for glycolysis, and I want to know what. I'm missing something, and I need to know what. What time is it? It's not 7 yet, is it? Oh, it's literally 2 minutes till 7. No, oh, no. Don't die. There we go. It's reconnected. Okay. I'm only gonna look... Okay. Okay. Glucose, 6 carbon, is phosphorylated by ATP, converting ATP into PI. Okay. That is the word that I forgot. Phosphorylation. Okay, so. Now, I made a big mistake here. It is then... Oh! Phosphorylated. Okay, so this is a 6 carbon compound. But it's unstable. So it quickly breaks down into 2GP. Or in other words, it's broken down into 2 free carbon compounds. Yeah. It's reduced by NADP. NAD. NADPH? I always thought it was NAD. I'm completely looking ahead. Sorry, I was looking at photosynthesis there. That's why I was so confused. Because that made no sense. So yeah, phosphorylated glucose breaks into that. 2-triose phosphate. Yes, this makes more sense. Then reduction of NAD. Oxidation of 2-TP into pyruvate. And then you get a net gain of 2 ATP. Okay, so from there, decarboxylation into acetate, so -1 oxygen. Sorry, no, it's decarboxylation. So that's a 3 carbon, that's a 2 carbon. Acetate combines with coenzyme A to become acetyl-CoA. From there, the citric acid cycle, or the carbon cycle, is where acetyl coenzyme A combines with... Okay, we can go the rest from here. So, this is a 2 carbon compound still. It's going to combine with a 4 carbon compound to become a 6 carbon compound, citrate. Okay, 6 carbon. From there, it is going to be decarboxylized into a 5 carbon, which is going to cause NAD to be reduced. Then from there, that's going to become a 4 carbon compound, which is... Yep, another... Then it becomes a 3 carbon compound, right? Oh no, just overall. Is it 1 ATP? Okay, so and then oxidative phosphorylation is kind of a whole other story. This is where NADH and FADH donate their electrons to the transport chain. The electron moves out, losing energy as it travels down the electron transport chain. The energy given off excites moves across the membrane. Gradient established, so ATP ADP moves down. Right. I will maybe come on to... Oh. Hello. I will maybe come back to oxidative phosphorylation. I'm glad we did that because it's been a while since we have done that. Jesus Christ, I miss so much. So, let's just go right from the start. We have glucose, which is phosphorylized by the reaction of ATP into ADP plus the inorganic phosphate. So it's still a 6-carbon molecule, but it's more reactive, so it breaks down into 2 3-carbon compounds. From there, those 3-carbon compounds are going to be oxidized, which causes NAD to be reduced into NADH. From there, there's still a 3-carbon compound pyruvate. They are then decarboxylized. Is that the right word? Yeah, decarboxylized into acetate. NAD becomes reduced because of this, NADH, and then acetate will combine with coenzyme A to become acetyl coenzyme A. So there's still a 2-carbon compound, then they're going to combine with a 4-carbon compound to become a 6-carbon compound. Right, my memory is back. There we go. Cool. So yeah, 6 into 3, into 2, 3, into 2, 3, into 2, 2, into 2, 4, which becomes 2, 6, 5, 4, and then back to 4 for the cycle. Okay. So, and what is this? Oh, it's the link. It's link. How did I forget about link? Wow. Okay, my head is crazy. Okay. So. Right. Conclusion. So. We have glycolysis, link, oxidative phosphorylation, and the citric acid cycle. So, how much ATP, how much NAD, how much FAD? So in glycolysis, we're getting +2, -1. How much NAD 1, FAD 0. Citric acid cycle is only going to make 1, I believe, but it's going to make 3 and 1, I think. Let's have a Google. Yeah, 3 NADH molecules. Cool. Sorry, I forgot to put an H there. Okay, so we have got that locked in. We remember this. Should we try and do the oxidative phosphorylation? Because I might remember this one better than I think. Oxidative phosphorylation is nigh identical, I think from what I remember, very, very similar to the electron transport chain in photosynthesis. So what we have is, it's going to be like, you know, something like this. Okay, so NADH is going to donate its electron, or hydrogen. It's going to donate its hydrogen, which is basically just an electron. So it's going to donate its electron. So they are going to donate their electron to the transport chain. It's going to move down the chain. And this is going to give off energy because it's going to undergo a series of redox reactions. That's easy enough. It loses energy, so it releases this energy. Because it's undergoing a series of redox reactions. The energy given off via these electrons moves the hydrogen, which I'm just going to draw here. It's going to move the hydrogen up the transport, going to move it across the membrane. This then establishes a gradient which is going to then, because there's a gradient established, hydrogen is going to move down the ATP synthase channel, which is going to cause ADP plus PI to become ATP. And finally, the oxygen is going to act as a terminal acceptor to accept the electrons. And it becomes H2O as a waste product. So, let's very quickly go through this from memory. So, NADH and FADH are going to donate their electrons to the electron transport chain. The electron will move down the transport chain, losing energy as it does so, releasing energy as it does so by undergoing a series of redox reactions. The energy released from these reactions is going to allow the hydrogen ions, they will be because they've lost an electron, H+, will allow the hydrogen ions to move through the intercellular membrane? What's it called? Inner mitochondrial membrane. It's going to allow them to move through the membrane, establishing an electrochemical gradient at the top. This gradient is then going to cause hydrogen ions to move back down through the ATP synthase channel protein, which will, as a result, cause ADP to combine with PI into ATP. Finally, oxygen acts as a terminal acceptor for the electron at the end of the chain, so it recombines into H2O, which is released as a waste product, which allows the electrochemical gradient to be maintained. That is science. Yeah. My arm hurts a lot after doing that. Oh, is there anything else? Honestly, there's not many processes for year 13, but the light-dependent reaction... The light-dependent reaction is almost identical. The energy given off from travelling electrons moves hydrogen across the membrane. Electrochemical gradient is established, moving it down the ATP channel protein. It's converted into ATP. That's almost identical. The only difference is photolysis, which is where photons will excite the electrons. It's split into H, and then the electrons, it loses it. The electrons move down the chain, the electrons are replaced. Cool, okay. I am happy to end things here for today, because we have just spent... We have literally just spent 40 minutes going through that, and I have happily revised. I am going to do some more work on the whiteboard though. I'm not going to stop there. In my own time for the next 10 minutes, I'm going to recap the two topics. So I'll see you guys in a bit. Goodbye.